Hi, everybody. Can I get you guys to stop talking, please?
You still do it? Yeah. It's free ice cream.
Excuse me, guys. Today, I'd like to start with taking questions from the chapter 7, or homework 7. We're in chapter 4. Taking questions from homework 7, so if you guys can take those out and take a look for me. While you guys are doing that, the plan for today, we've been talking about solving here in class. Today we're going to kind of finish up with that idea. So we're going to add in the last little pieces that we need to complete the solving picture. We'll do some factoring practice again, and that'll kind of wrap up our day. But we'll start here with questions from homework 7. Ben, did I see your hand up?
Yeah. Can we do number 14 then?
Okay. Sure. So, for 14, first thing I need to do is get it equal to 0 if I'm going to apply the quadratic formula, which is what the directions ask for. So I'm just going to subtract 1 from both sides. And then I'm going to note the values for A, for B, for C, and fill those in now to the quadratic formula. So negative B, square root of B squared minus 4 times A times C, all over 2 times A. And now I'm just going to be simplifying things down. So 48 squared minus 4 times 64 times 9 gives me 0 over 128. Oh, good.
No absence, no online school for me.
Okay.
Is that a 69 where it's like right under the bird part? Oh, sorry.
It's the A value from the problem that we wrote down earlier.
Oh, okay.
So I reduce this down, and this is negative 3/8. Well, the square root of 0 is just 0, and anything plus 0 is 0, and anything minus 0 is, like, it doesn't change anything. You know what I mean?
Thank you.
Yeah, no problem, my man. Okay, who's next? Hallie. 8? Sure. Okay, so the first thing we'll do is we'll get everything combined into one location. So I'm going to subtract x squared from both sides, and then I'm going to subtract 10 from both sides, because this is something I'm just using the reverse order of operations for. So I want to just start by getting the x's on one side and the constants on the other. Okay with that? Then we can divide by 2. And then we'll square root both sides. So when we square root both sides, that creates the plus or minus. Stop talking, please. The square root of a fraction is the square root of the numerator over the square root of the denominator. The square root of 1. And then we agreed that we didn't want to leave square roots in the denominator of our fraction, right? So to fix that, I'll just multiply the top and bottom by the square root of 2. The reason that works is because the square root of 2 times the square root of 2 is the square root of 4, which is just 2. Okay with that, Hallie? You might have recognized square root of 2 over 2 from geometry last year. That was the sine and cosine of 45-degree angle. If that number looked familiar. Ava? Sure.
I feel like those ones are a lot easier than like the ones.
Okay. So number 10, we'll start, again, reverse order of operations. So we'll subtract 13 from both sides. And then divide both sides by 2. Negative 2, I should say. So far, so good, Ava? Okay. And then we'll square root both sides. So that, because when we square root both sides, we get a plus or minus. And then we'll break that square root across the fraction. And then we'll add the 6 over. I divided both sides by negative 2.
Oh.
That's okay. It just took me a minute to kind of figure out what step you were asking about. The 2, I'm like, the 2 didn't go anywhere. It's still hanging around, just in the denominator now. So there's that. Okay with that, Ava? Okay. And then we, again, don't like that square root in the denominator. 13 times 2 is 26. And then usually in a situation like this, we'd make a common denominator and write this as a single fraction. So 6 is the same thing as 12 over 2. So this would probably be the way that it would appear on like a multiple choice test or something. But it's not any more correct than the previous answer was. I wouldn't make any difference between the two of them. Is that okay? Of course. Any others? Happy to do more. Okay then. What we'll do now is we'll do a factoring practice. So I'm going to pass out a factoring practice sheet. When you get this, just leave it face down on your desk. So I tell you to do so, then you can flip it over and get to work on it. As always, if you need something to write with, you can use a calculator if you want. All the problems can be done without a calculator if you don't have one. This sheet includes things that you can use a shortcut on, things that you can't use shortcuts on, and some things that aren't factorable at all. So it's a little bit trickier, but that's okay. I'll give a little bit more time on this one. We'll give you 5 full minutes to work on this. Keep in mind that there are things that you have to do the long factoring method on. There's things that you can use the shortcut on. And there are things that can't be factored at all using our methods. So just kind of be cautious there. For those of you that are working from home, you'll see factoring or time factoring practice number 7 in the content library. You can pull that and work with us at the same time, or if you don't get it quite started on time, you can certainly time yourself and participate when you're able to. But we're going to work on this for 5 full minutes, and then we'll do we'll go through and figure out how many we did and how many we got right and all that jazz, just like we normally do. Everybody ready? On your marks, get set, factor. Yeah, I thought it was funny.
Bless you.
Thank you.
You're welcome.
Just a few seconds left here, folks. And pencils down. Okay. Quick show of hands on how many we got finished. At least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Some of us were confused by what I meant there. All right. So that's good. Sounds like basically we're working at the same rate we were before. These were a little bit trickier because there were some things in here that you hadn't seen a lot of. Let's run through the answers here. You guys, again, check your own. Again, there's no penalty for not finishing or getting things wrong or any of that. This is just practice for you. So here's the first 6 or so. I give you guys a minute to kind of check these, and then I'll scroll down so you can check the rest of them. You guys ready for me to scroll? Okay, there's the rest of it. All right. Quick show of hands. At least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it seems like more or less the ones that we're finishing we're doing correct within 1 or 2, which is good. Yeah, so keep up the good work. We'll continue to kind of do practice with this. But for now, we're going to go back to solving. And
is this test like for this chapter gonna be like a longer test than usual? Like, I don't know if that is actually a good question to ask.
I mean, I haven't even started writing the test yet because we're like not even really that close to being finished.
Yeah.
So about the test, one little bit of what I'm going to put on it. I mean, I have an idea already, but you get what I mean. Like I haven't sat down and started to write anything yet. Hallie, of course. Okay. So last time we met, we spent a lot of time talking about Samar solving. So we talked about solving by factoring. We talked about solving by using the reverse order of operations and then using the quadratic formula. And we had basically said that's it as far as the techniques goes, and that's true, but there's still a little case kind of lingering. Actually, it's not really that little of a case, a pretty big case. That we're still not quite prepared to deal with. So let's say that we have this problem here. X squared plus 1 is equal to 0. To solve that, what would we do? Well, I would use the reverse order of operations here, right? So we'll just start by subtracting 1 from both sides. And then we'll take the square root of both sides. And now, because we took the square root of both sides, we create a plus or minus. But does anybody see anything funny going on with what we've just written down here? Yeah, we're taking the square root of a negative number. Is that a problem? Yeah, so right. Now, we're going to fix that here in just a moment. And it's going to feel kind of like you're just doing some funny stuff right now as you're about to fix this. But I want to remind you that what we're about to do, we've done like, or you guys have done already like 3 or 4 times in your mathematics education. So remember back to elementary school, and you started learning about subtraction. Eventually you did something like 3 minus 4 and had to define a new set of numbers called the negative number, so you're able to do that problem, right? And then a little bit later, when you started learning about division, you divided stuff like 3 divided by 4, and you had to define things called like fractions, so you could deal with that sort of thing. And a little bit later on, you had to do things like the square root of 5, and you had to define a new set of numbers to deal with these things that couldn't be written down like fractions, like square roots of 5. So a bunch of times we've gone and like added new numbers to our set of numbers we work with, So they're able to do more kinds of problems. We're about to do that right now so we can finish doing a problem like this. Because you're right, the square root of -1 is not a real number. And now when I say real, I don't mean like because it actually exists or something. We're talking about like the set of real numbers. Remember when we defined number sets back in the first couple of weeks of school? We had like integers and rational numbers and real numbers. That's what I mean by real number, not like it's made out of stone and it's sitting in the corner so I know it's real. So we're going to define So we're defining this new set of numbers called the complex numbers. The complex numbers are of the form a plus bi, where a and b are just real numbers, and I is equal to this square root of -1, and we call I the imaginary number. So if we go back to that working on before, with this new definition, we'd say that x is equal to plus or minus I. And that's how we'll write our answer there for that. Now, before we go back to solving here, we're going to take a slight little detour because we've defined this new set of complex numbers. We need to spend some time talking about the complex numbers and getting familiarized with those so that we can use them reasonably. So we're going to talk about, determining if something's a complex number or not, picking out the values for a and b, adding, subtracting, multiplying, dividing, absolute value, all that good stuff with how we do that with complex numbers. And then we'll circle back to solving here at the end of class. Okay? So for this first set of examples, we're just going to determine if something's a complex number. And if it is, so let's say we have 5 plus 4i. Is that a complex number? No.
Oh, my bad. I thought that was a 0. No.
So again, to be a complex number, it has to fit that form, right? So this is a complex number, right? What's the value for A? And what's the value for B? How about 3 minus 6i? Is this a complex number? Sure it is. We can just think about it as 3 plus -6i, where a is 3 and b is 9. Everybody okay there? Okay. What if we have 2 plus 3i over 5? Is this a complex number?
No.
Sure it is. We can rewrite it as 2/5 plus 3/5 I. So sure, that's a complex number. 2/5 and b is 3/5. How about minus 3i? Is this a complex number? Stop talking, please. Is this a complex number? Yeah. We can write it as like 0 minus 3i. How about 6? Is this a complex number? Well, yeah, it is. We can think about this as 6 plus 0i. You are the only one that's saying anything, and I appreciate that. The A is the part with the I attached to it?
No, like, how do you know it's square root of negative 1? How do you know that, like, 6 isn't?
Because it doesn't have the I attached to it.
Well, neither does the other one. You can't see it. Then it's just 0.
What is the other one?
Like 0. And they said no and I. She's talking about the negative 3i. No, I'm not. I'm thinking about E. With the E.
There's a 0. There's an I next to the 0.
Yeah, so
How do
zero.
we know?
Because it's right next
It's
to
just a formula. I think it's just the second number.
Yeah, you're just putting in the zero, so you have something to be.
Yeah, so it's a complex number. 6 plus 0. I see.
So the takeaway here is, what can we say as the big overall takeaway of this? Everything is a complex number, right? Which is what should have happened, right? If you think back before, when we created like the integers, you had positive numbers, you added on the negatives, but everything was an integer, whether it was positive or negative. We had the integers, then we added on the fractions. Everything was a fraction, whether it could be written as a 7 or 7 over 1. We could always write it as a fraction, right? And then we go on and on. That's what should happen when we extend these things. We want everything to be part of the extension. So that's the takeaway. Is everybody okay with that idea? Okay. I didn't want to spell that out at the beginning. I wanted you to kind of see it for yourself and convince yourselves that, like, okay, I see what he's doing here. Like, everything is a complex number. I can just, look at it the right way, and it's like, okay, sure. So let's talk about operations now. The first operations we'll talk about are addition and subtraction. Okay, let's say we have the complex number 3 plus 2i plus the complex number 5 minus 7i. To add two complex numbers, it's very easy. We just add the real parts together. So 3 plus 5 is 8. And we add the imaginary parts together. 2i plus negative 7i is negative 5i. Basically, all we're doing is combining like terms, right? We're treating the I just like we would a variable, and just combining the like terms. No big deal, right? Pretty easy. What if this was subtraction? What's the thing that we have to be careful about here with if it's subtraction? What was double? Yeah, so this negative is like distributing through. So really we have like, yeah. So that's going to be 3 minus 5 is negative 2. 2i and 7i is 9i. Good? Yep. So again, should be pretty easy to do, right? No big deal there. Addition and subtraction is pretty straightforward. Let's do some multiplications. if we have 5 times 2i minus 3, or I'm sorry, 2 minus 3i? What do you suppose we do here? Yeah, we just distribute. So 10 minus 15i. That's nice, right? Works exactly as we'd expect it to. What if we have 3i times 5 plus 7i? Well, it's going to be 15(1i) squared, because you have I times I. But what the heck does I squared mean? So let's take a little aside and deal with that. So remember, I was the square root of -1, right? So I squared is the square root of -1 squared. The squared is going to cancel the square root, leaving us just with -1. So we should keep going here on this previous problem. And replace that I squared with a -1. So really we have -21 plus 15i. So that's an important result there, that I squared is -1. We'll use that quite frequently when multiplying or dividing, as you'll see in a few minutes. But overall, still not difficult, right? Looks very much like what we've been doing. What if we have 3 minus 2i times 6 plus 7i? What do you suppose we should do for this? Yeah, we're just going to FOIL it. So 3 times 6 is 18. 3 times 7i is 21i. -2i times 6. And -2i times 7i is -14i squared. So we can combine like terms. 21i minus 12i is 9i. And we know that I squared is equal to what? -1. So -14 times -1 is +14. And 14 plus 18 is 32. So still no big deal, right? Works basically exactly the way we'd hope it would. You know, all this stuff is on Power or on OneNote also, right? So even if you miss a thing here or there, it's not the end of the world. You know, you can always go back and look at it later. I'm just reminding you. I know it's easy to forget that.
Mr. Cool popping out today in the Kill Streak.
I'm just reminding you guys, because I know that we forget on these things, right?
You might be inbound.
It's not a big deal. You guys are being awful hard. So the next thing up is division. So let's look at some division examples. Also worth noting that this is the same thing as like saying something like this, right? Everybody's okay with that notion that we can write as a fraction or as a division problem? Typically we write these as fractions, but they mean the same thing. So just like we did before, we can just do 2 minus 3. Right? No big deal there. Okay. How about if this happens, if we have an I in the denominator? If we separate it out, like we did the previous one, we're still going to end up with an I in the denominator, right? And that's not the form for a complex number. A complex number can't have an I in the denominator. But we can fix this relatively easily. So the way we fix this is we're just going to multiply the top and bottom by I. What effect is that going to have? Well, the I distributes to the numerator, and it just multiplies to the denominator. So I have 6i plus 5i squared over 3i squared. And remember, the I squareds we can replace with 1. And now this looks just like the previous problem, right? So I can write -5 over -3 plus 6 over I. Or if we simplify this down, 5/3 minus 2i. Everybody okay there? So the trick there, multiplying the top and bottom by I, got rid of all the i's in the denominator, right? Joseph? Sure. Let's do one more. So here we have 3 plus 5i divided by 2 minus 7i. Will that same trick work here if I multiply the top and bottom by I? No, right? Because when I distribute, I'll have 2i minus 7i squared, and I'll still end up with an I in the denominator. So we need a different trick when we have a fully complex number and not just the imaginary part. Here's the trick that we use. We're going to multiply the top and bottom of the number by the conjugate of the denominator. So the conjugate is the term for that, where it's the same thing, but it just has a different sign in the middle. So if I had a 2 plus 7i, the conjugate would be 2 minus 7i. It's always just the opposite sign, and it's only the thing in the middle that we worry about. We don't change both of the signs, just the thing in the middle. So now what we have is just two foiling problems, right? Numerator, I have 6 plus 21i plus 10i plus 35i squared. In the denominator, I have 4 plus 14i minus 49i squared. So just FOILed that stuff out. Now let's combine like terms and replace our I squareds with negative ones. So 21 and 10 is 31i. And I squared is negative 1. 14i and negative 14i is 0. And we'll replace our I squared with negative 1. Notice what happened in the denominator? All the i's canceled out. There's no more i's down there, right? Okay. So 35 times negative 1 is negative plus 29, or plus 6 is negative 29. 4 minus a negative 49 is 53. Neither of which can reduce, so I'm done. Again, not so bad, right? Not a big deal. Little bit of work to do, but it's mostly just skills that we've already established. Yes, of course. Haley. That's just me double checking. I have to practice or I forget. Yeah, okay.
You know what my name is recorded?
Yeah, I used it already today, Ben. I go out of my way to try to use people's names, or else I forget them, you know? All right. And the last operation that we're is the absolute value. So before we describe how to do this, I want to ask you guys a question. Which of these two complex numbers do you think is bigger?
The second one.
It doesn't really make sense, right?
Yeah.
Like if you were trying to arrange these on the number line, which one would go before which one? Right? Like that doesn't really make a lot of sense. And the reason is because we really have two components to a complex number, right? So we can't arrange these on a number line. What we'd have to do is we're going to have to arrange them in a two-dimensional space. So for example, 3 plus 2i would go 3 over on the real axis, and then 2 up on the imaginary axis. So there would be where like 3 plus 2i would go. And then 2 plus 3i would go 2 over and 3 up. So in order to kind of place these in relation to each other, we need to use a two-dimensional space. Everybody's okay with that idea? Now, if you remember all the way back to when we talked about absolute values, the basic definition we gave for an absolute value was the distance that number is from 0 on the number line. With complex numbers, we're not using a number line, we're using a plane. We're using this two-dimensional space. So the distance, say, from 2 plus 3i back to 0, which would be the origin, is that line there, right? Well, I can find the value by making a right triangle where I went 2 over and then 3 up. And how do I find the third side of a right triangle? Oh, you did it last year so many times. This is the one thing from geometry no one should have forgotten. The Pythagorean theorem. Yes. Yes, a squared plus b squared equals c squared. So we say the absolute value then of a plus bi is just the square root of a squared plus b squared. So that's the formula. We'll use that like every time. So if I was to do the absolute value of 4 minus 5i, all I'm going to do is the absolute value of 4 squared plus the absolute value of negative 5 squared, which would be 16 plus 25, or the square root of 41. And we're done. Everybody okay there? No big deal, right? Now, rather than just presenting you that formula and going, that's the formula, we built up to it a little bit by kind of justifying where we're getting that from, why all of a sudden is the absolute value not just like dropping negative signs off. So I do this because I think it helps make it easier to remember why it's not just dropping negative signs. But that's all we're doing. Everybody okay there? Okay. So that's all we needed to do operations-wise for complex numbers. We now can add, subtract, multiply, divide, and do absolute values for them. So we have everything we need in order to kind of deal with basic complex number operations. So let's return back to solving. So let's say we want to solve x squared plus x plus 1 equal to 0. How should I solve this? Well, first thing I would try to do is to factor this because it's in a convenient form for it to factor. Is this factorable? Are there two numbers that multiply to give me 1 and add to give me 1? No. Okay. So if it's not factorable, how am I going to solve it? Ava. I use the reverse order of operations when I have one kind of x. Here I have x's and x squared, so I wouldn't want to use the reverse order of operations here. We have one more choice. The quadratic formula. Okay. Yeah, but I don't sing. Yeah, I don't sing.
X, Y, Y.
It's so, yes, Ava. Of course. So there's the quadratic formula. One squared is 1. 4 times 1 times 1 is 4. 2 times 1 is 2. 1 minus 4 is negative 3. And now we've run into that problem, right, where we're trying to square root a negative. But that's okay. I can think about the square root of negative 3 as the square root of negative 1. 3. Right? Why would I want to do that? Because the square root of negative 1 is equal to I.
Did that hurt your eye? You kind of want to hit your eye. I don't know.
I cupped it.
It still hurts.
And there's my answer. Okay with that? Let's do another example. Sound good? Let's do that. Okay. How do I want to solve this one? So you're going to use the reverse order of operations, which is what it sounds like you're starting to say, which is correct. That's what I'd want to do. So we'll start by subtracting 10. That's good. Okay, and then what? Great, then we'll divide both sides by -2. Next up would be to square root both sides. Because we've square rooted both sides, that creates a plus or minus. Because we're square rooting a negative number, that means we're going to get I square root of 4. So basically all that we're going to do is the negative sign under the square root just becomes an I in front of the square root. No big deal. And what's the square root of 4? Write that as plus or minus 2I. Everybody's okay there? And my last step then would just be to add the 7. Can I add 7 to 2I?
No.
No, so I'm just going to write it next to each other. And there's my answer. What do you guys think?
Looks good.
It's not much different than what we did yesterday, right? The only little difference is when we get these negative signs underneath the square root, we just kick the negative out to the, or we kick out the negative and put an I out front, right? That's all that's happening. It's the only thing that's changed. We did all that work just to put some I's in here where we got negatives under square roots. Well, it was an important digression to get to there. But now every quadratic is solvable. We have different methods that are more effective depending on the form that it's written in, but every quadratic is now solvable. We'll get no solution for nothing. All of them have solutions. That's awesome. Okay, we're going to stop here.